Okay, think about this for a second. We use the word law all the time, right? Like the law of the land or, Murphy's Law.
Very common word.
But then you take that same word into science, and it suddenly feels like it should mean something absolute, foundational, like bedrock truth.
It carry that weight.
But what if, even in science, not all laws are really the same? What if some are, well, more law than others?
That's exactly the idea we're digging into today. It's fascinating stuff, actually.
So for this deep dive, we're looking at some work by Dr. Nimrod Israeli.
That's right. Specifically, his piece, What is a Universal Law and Why Most Laws Aren't? Part 1.
Right.
And our goal, really, is to get clear on what makes a scientific law truly universal.
Okay.
And crucially, why that distinction matters so much for, well, everything, from physics right up to how our societies work, or perhaps why they sometimes don't work as we expect.
And it sounds like we might find that some things we learned as laws in school maybe don't quite hit that universal mark.
Precisely. They're often incredibly useful, don't get me wrong, but maybe only within a specific context.
Right, so this isn't about tearing them down, but about getting a sharper understanding.
Exactly. Think of it as a shortcut for you, the listener, to get really clear on this critical distinction that, honestly, often gets glossed over.
Okay, I'm ready. Let's get into it. Where do we start? Unpacking the language.
Yeah, let's start there. Because Dr. Israeli really hammers home how important the words are. A principle. That often holds true, right?
Usually, yeah.
A law starts to imply some kind of necessity, like it has to happen that way.
Okay.
But a universal law, now that's a huge claim. That suggests a pattern that holds true across all time, all space, all scales of reality. It's profound.
So what does that level of precision actually, buy us? Why does it matter so much?
Well, it matters because it shapes how we see the fundamental workings of nature. And that shapes how we try to build things, whether it's technology or societies or, paths to prosperity.
Right.
When scientists talk about things like gravity or entropy, the second law of thermodynamics, or energy conservation, these aren't just like neat ideas.
No, they feel fundamental.
They're fundamental. They're seen as the bedrock, the deepest architecture of nature. They define the absolute rules, what's possible, what's constrained, what's just flat out forbidden by the universe.
They're the operating system.
That's a great analogy.
Yeah.
They're not suggestions.
Okay, but here's where it gets tricky. You mentioned earlier, not all these laws are equally universal. That feels counterintuitive.
It does, doesn't it? But that's the core idea Dr. Israeli is exploring. Some laws really do seem to apply everywhere, always. Think fundamental physics.
Like EMU-MC.
Exactly, or gravity.
Yeah.
But others, even ones we call laws and teach in schools, well, they only really work perfectly under certain conditions or within specific fields. And here's the really crucial insight. As we go up the ladder of complexity, from basic atoms to molecules, then cells, then whole ecosystems, and finally societies, the clarity and the universality of these rules seem to, well, weaken. What starts as absolute necessity in physics becomes more like probability in biology.
Okay, I can see that.
And then when you get to the social world, it often feels more like just a tendency. It's like the rule book gets fuzzier and fuzzier.
Wow. Okay, so if I'm following this, that fuzziness, that weakening clarity has huge consequences.
Absolutely huge.
You're saying the reason we've made such incredible leaps in physics, chemistry, electronics, medicine, it's because they rely on these super predictable universal laws.
Largely, yes. That predictive power is key.
But then, and this is the kicker, the social sciences just don't have that. They lack a comparable foundation.
That's the argument. We don't seem to have a single, universally agreed upon scientific law that explains how a community must behave or how a company must evolve or why a society holds together or falls apart, or even how complexity itself works.
That's sobering, especially when you think about trying to solve massive problems like poverty.
Exactly. It means our solutions are often very context-specific, maybe even fragile.
Like treating symptoms because we don't grasp the underlying system's rules.
Precisely. We lack that foundational, universal framework for complex systems.
So if that foundational strength weakens as we move up in complexity, what would it even take for a law to be truly universal, to span everything from atoms to societies? What's the standard?
Well, he argues it has to describe a structural regularity. Something that holds true no matter what, across all time periods,
Okay.
all locations in the universe.
Right.
And crucially, across all layers of reality, physics, chemistry, biology, society. It can't just apply in a lab or only on Earth.
It has to define invariant relationships. What does that mean exactly?
It means it sets the absolute boundaries, what's fundamentally possible, what's constrained, and what's completely impossible, regardless of the specific situation. It's about the underlying structure of reality.
Okay, so how do we actually check if something meets that incredibly high bar? Dr. Israeli outlines 4 key properties, right?
It's 4 non-negotiables.
Let's go through them. First is timelessness. So it had to be true right after the Big Bang. And we expect it to be true billions of years from now. It's not temporary.
Correct. Eternal, essentially. Then second, spatial generality. It works here. It works near Alpha Centauri. It works in galaxies we can't even see, everywhere.
No geographic limits. Okay. Third, and this is the one that really jumps out, cross-domain validity.
This is the big one for complexity.
Yeah, it has to operate not just in physics or chemistry or biology alone, but across all of them, including society. That feels like a massive leap.
It is. It implies a deep unity across seemingly disparate fields. And finally, number 4 is structural necessity.
Okay.
This isn't just about what usually happens or what's likely. It defines the absolute outer limits, what must occur or what cannot occur given certain conditions. It's about the constraints imposed by the universe itself.
Wow. That is a very high bar.
Extremely high.
Okay.
And it really echoes how scientists like Richard Feynman viewed genuine laws. You start with a guess, a hypothesis.
Right.
You figure out what logically follows from it, what its predictions are,
And then you test it.
rigorously
Yeah.
against observation. And for a universal law, those tests have to hold up in physics and chemistry and biology and human social systems.
Okay, so when you apply that filter, that incredibly demanding standard, how many laws actually make the cut? It sounds like maybe not that many.
You're right, the list gets pretty short. Think about Newton's law of universal gravitation.
Apples and planets.
In galaxies, it works across incredible scales. Or Einstein's Einstein and general relativity, they describe the fundamental relationship between mass, energy, space-time.
From the smallest scales up to black holes.
Exactly. Then you have the laws of quantum mechanics governing the subatomic world, also seemingly universal within their domain.
And thermodynamics.
Ah, yes, the second law of thermodynamics, entropy always increasing in a closed system. That feels deeply, fundamentally woven into reality itself, doesn't it?
It really does. Okay, so these are the heavy hitters, the truly universal laws.
They seem to be, based on this strict definition, they're like the structural beams of the cosmos.
So what about all the other laws we learn? The ones that are staples of, say, biology or chemistry or even economics. Where do they fit in if they don't meet this standard?
That's the crucial distinction. Many of those are better described as conditional or contextual rules, meaning they are incredibly useful, often highly accurate, but only within certain boundaries or specific contexts. They don't have that universal cross-domain validity.
They work, but only under the right circumstances.
Pretty much. They help us organize knowledge within a field. They describe patterns that are often reliable there, but they don't define those absolute structural boundaries of what is possible in the same way.
They're more like local ordinances than the constitution of the universe.
That's a perfect way to put it. Excellent analogy.
Okay, so give us some examples. Which familiar laws fall into this conditional rule category? This might challenge some assumptions.
Definitely. Let's take Mendel's laws of inheritance in genetics. Hugely important.
Absolutely foundational for genetics.
But they don't really apply to bacteria or viruses, which reproduce differently. And they don't account for more complex things we now understand, like epigenetics or gene linkage. They work for specific, simpler inheritance patterns.
Okay, so context dependent. What else?
How about Boyle's law? PV, constant for gases.
Yeah, chemistry class staple.
Works great under ideal conditions, moderate temperature, moderate pressure. But push the gas to extremes, or look really closely at the individual molecules, and the law breaks down. It's an approximation.
Approximation, right.
Kepler's law is describing how planets move. Brilliant for his time. But then Einstein's general relativity provided a deeper, more universal explanation based on space-time curvature.
Oh.
Kepler's laws became a specific case within a bigger framework.
Okay.
Ohm's law in electricity, VIR, essential for basic circuits. But try using it with really high-frequency signals, or in materials that don't conduct electricity linearly, and it fails.
Right. There are limits.
And here's one that often sparks debate. The so-called law of supply and demand in economics.
Ah, yes. Often presented as the fundamental law of markets.
Exactly.
Yeah.
But think about real-world markets. Are they always rational? Do monopolies or government regulations or just plain human psychology not constantly interfere with that simple relationship?
All the time.
So it often collapses under real-world pressures. It describes a tendency, perhaps, in an idealized model, but it's hardly an ironclad universal law of behavior.
So again, it's not saying these rules are wrong or useless.
Not at all. They're incredibly valuable tools within their proper scope.
It's just about clearly classifying them and understanding their limitations. Does recognizing this change how scientists should work in those areas?
That's a deep question. I think it encourages humility and maybe pushes researchers to look for deeper, potentially more universal principles that might underlie these conditional rules.
And circling back to Dr. Israeli's main point, this distinction really throws into sharp relief that missing piece, doesn't it?
It absolutely does, that void. We have laws for falling objects, chemical reactions, even subatomic particles. But we seem to lack a widely accepted, fundamental scientific law explaining how complexity itself emerges, sustains itself, and sometimes catastrophically collapses, whether that complexity is a star, a cell, an ecosystem, or a civilization.
We can predict eclipses with incredible accuracy.
Decades, centuries in advance.
But we struggle to predict why one company thrives and another identical one fails, or why a society might suddenly unravel.
Exactly. It feels like a massive blind spot, a missing pillar in our scientific understanding of the universe, especially the parts we inhabit most directly.
Okay, so if we have this missing pillar and this idea that laws get, as you said, fuzzier as things get more complex, what does that imply for how knowledge itself is built? How should we think about the relationship between, say, physics and sociology?
It suggests that reality and our knowledge of it unfolds in layers. It's like building upwards.
How so?
Physics provides the absolute foundation, the universal laws of matter, energy, space, time. Chemistry emerges from physics using those laws, but creating new patterns with molecules.
Right, built on top.
Then biology emerges from chemistry, constrained by both physics and chemistry, but generating life's incredible complexity.
Okay.
And finally, things like societies, cultures, technologies emerge from biology, still ultimately grounded in the laws of physics, but exhibiting radically new kinds of behavior.
So the lower level laws don't disappear. Gravity still applies to societies.
Absolutely. Foundational laws persist all the way up. Their effects just become part of a much more intricate, interwoven system. You can't violate physics, even in sociology.
So if these layers are all connected, all ultimately resting on that physical foundation, here's the big leap. What if there is a law that governs that very process? The process of building complexity itself.
Now you're getting to the heart of it.
Not just as a nice idea or an analogy, but as a genuine structural necessity that applies to all complex systems.
That's exactly the possibility Dr. Israeli points towards, the idea of a potential law of complexity. Something that could unify how galaxies form, how life organizes, how ecosystems function, how civilizations rise and fall, seeing them all as different expressions of the same underlying dynamic.
A law that governs emergence itself. That's huge. It's almost dizzying to think about.
It is, and crucially, such a law wouldn't cancel out physics or biology. It would work with them, clarifying why complexity emerges under certain conditions and fails under others.
It would explain stability and instability.
Exactly. Why do some systems hang together and adapt while others just dissolve? It could identify the universal requirements for enduring complexity and the thresholds beyond which systems become unstable.
Let's make that concrete. How might this apply to something like poverty? You mentioned it earlier.
Okay, yeah. So we usually frame poverty as an economic problem or maybe a social justice issue, right?
Yeah, sure.
But viewed through the lens of a potential law of complexity, poverty might be seen as a structural outcome, a state a system gets into when certain universal conditions aren't met.
What kind of conditions?
Things like, is there a sustained, reliable input of energy, which could be food, money, information, opportunity?
Yeah.
Is there coherent internal organization and structure within the community or household?
Okay.
Is there a clear shared sense of direction or purpose? And critically, does the system have a way to effectively release waste, disorder, or surplus energy outwards?
So energy in, structure, direction, flow out.
Right. And the mind-blowing part is these same fundamental requirements, energy, structure, direction, flow, seem to apply whether you're talking about a thriving cell, a stable ecosystem, a successful company, or a flourishing community.
It's the same pattern at different scales.
That's the proposition, that these aren't just social factors, they are structural realities governed by universal principles.
Mm-hmm.
If we ignore that, we just keep treating the symptoms lack of money, poor housing without addressing the underlying systemic failure to meet these universal requirements for complexity and stability.
That really reframes the problem entirely, from just economics to fundamental system dynamics.
It does. It suggests a deeper, more unified way of understanding why things work, or why they don't.
Okay, so this has been quite a journey. We started by questioning what law really means in science, realized not all laws are universal.
Right, distinguishing universal laws from contextual rules.
Identified that very high bar for universality, saw how few laws actually meet it, and recognized this potential missing pillar regarding complexity. And now we've arrived at this really provocative idea of a unifying law of complexity that might span everything.
Exactly. And Dr. Israeli hints that his next article will actually lay out this proposed emerging law.
Oh, really? He puts forward a candidate.
He does. And he suggests it has 4 essential components. And when you hear them, you might start seeing them everywhere.
Okay, give us the preview.
He identifies them as 1, a sustained input of necessary energy or resources.
Right.
2, the presence of coherent internal structure and organization.
Got it.
3, the clarity of a shared direction or goal. And 4, the capacity to release surplus, waste, or disorder through some kind of outward flow.
Energy, structure, direction, flow.
Yes, and the key claim is that these aren't just abstract ideas. They are observable, repeatable, and measurable features of all complex, enduring systems, from stars to startups.
That's incredibly ambitious, but also potentially incredibly powerful if it holds up.
It really is.
So here's a final thought to leave everyone with. We have these incredibly successful laws for how things move, how heat works, how life replicates.
Newton, thermodynamics, DNA.
Right. But maybe the next great scientific revolution, the law we're desperately searching for to understand our complex world and solve its biggest problems. Maybe it's not another law of motion or matter. Maybe it's a law of emergence itself.
A law of how complexity comes to be and how it persists.
Yeah. So as you go about your day, maybe start looking at the systems around you, your workplace, your community, even your own life, through that lens. Energy, structure, direction, flow. What makes things work? What makes them fall apart? Could there be a universal pattern there?